All right, let's dive in. Today, we're cracking a chemical code. We've all heard of the pH scale, these simple numbers from 0 to 14. But what you might not realize is that those numbers are basically a secret language for something much more complex happening inside a solution. So, it's time we learned how to speak it.
So let's start with this. Lemon juice is acidic, it has a pH of 2. And bleach, that's super basic, with a pH of 13. But what does a 2 or a 13 really tell us? I promise you, the difference between them is way, way bigger than you think. And by the end of this, you'll know exactly how to measure it.
You see, pH is basically this universal language. It was invented to take these ridiculously huge, kind of messy numbers for ion concentrations and just simplify them. It translates all that complex chemistry into a single, easy-to-understand number. And you see this language, well, everywhere. From the juice you drink in the morning to the soap you wash your hands with, everything has a pH value. But these aren't just random labels. They're telling a very specific story about what's happening at a molecular level. And the name itself gives us a huge clue. pH literally stands for the power of hydrogen. The P is just a math symbol for take the negative log, and the H, well, that stands for the concentration of hydrogen ions. That little formula is the key to this whole thing.
So let's talk about that power. This is probably the single most important thing to get about the pH scale. It is not a linear scale. It's logarithmic. That means a change of one little number is actually a massive leap in acidity.
So, check this out. We've got a solution at pH 4 and one at pH 3. They look super close, right? I mean, it's just one number apart. But in the world of chemistry, that single digit represents a colossal difference.
And here's why. Because it's a logarithmic scale. Every single step you go down the scale means a tenfold increase in those hydrogen ions. So a solution with a pH of 3 isn't just a little more acidic, it's 10 times more acidic than one at pH 4.
This quote from one of our sources just nails it. If you go from a pH of 5 down to 3, that's 2 steps, right? So that's not 20 times, it's 10 times 10. It's 100 times more acidic. This exponential power is why even tiny shifts in pH can have huge consequences.
Okay, so if pH is just a code for the ion concentration, how do we crack it in reverse? How do we take that simple number and turn it back into the actual, raw concentration of hydrogen ions? Well, that's what we're about to do.
This, right here, is our master key. The concentration of hydrogen ions, that's what the brackets around H+ mean, is equal to 10 raised to the power of the negative pH. This one little formula unlocks everything.
Okay, time to grab your calculator. Seriously, go find it. We're looking for one specific button. Find your log button. Now look right above it. You should see a little 10 to the x. That's the inverse log function, and it's going to do all the heavy lifting for us.
Let's walk through one together. Say we've got a solution with a pH of 8. First, you hit Shift, then Log to get that 10 to the x function on your screen. Now here's the part everyone forgets. You have to enter the negative pH value, so for a pH of 8, we type in -8. Hit Enter, and bam! There's your answer. 1 times 10 to the -8 moles per liter. See that? The pH was 8, and the exponent in our answer is -8. That's the direct link. You just cracked the code. It's that simple.
But wait, there's more. Hydrogen ions aren't the only players in this game. In any solution with water, there's a balancing act going on with another ion, the hydroxide ion. And just like pH, hydroxide has its own scale, called pOH. It's the other side of the coin. And here's the really beautiful part. At room temperature, pH and pOH are always connected by this super simple rule. They have to add up to 14. This is an awesome shortcut, because if you know the pH, you can find the pOH instantly just by subtracting from 14.
All right, this is it. Time to put everything we've learned together. We've got our main formula, we've got our pOH shortcut. We're going to take a single piece of information and use it to figure out the entire chemical story of a solution. So here's our mission, straight from the source material. We've got a solution of sodium hydroxide, and the only thing we know is that its pH is 9.3. Our goal? Fill in the rest of this entire table. First up, let's grab the low-hanging fruit, the pOH. We just use our shortcut. 14 minus our pH of 9.3 gives us 4.7. And just like that, the first piece of the puzzle is in place.
Okay, next up, the hydrogen ion concentration. We go back to our master formula, which is 10 to the negative pH. So we plug in 10 to the power of negative 9.3. Punch that into the calculator and you get 5 times 10 to the negative 10th molar. Second blank, filled.
And for the final piece of the puzzle, the hydroxide concentration. It's the exact same idea, but this time we use our pOH. It's 10 to the negative pOH, so 10 to the power of negative 4.7. That gives us 2 times 10 to the negative 5th molar. And look at that! The table is complete. We got the whole story from just one number.
So you might be thinking, okay, cool math, but why should I care? Well, this stuff is everything. It's not just a number in a chemistry class. In biology, the enzymes in your body will only work if your pH is just right. In environmental science, the low pH of acid rain can devastate entire ecosystems. And in chemistry, it's one of the master controls for how fast or slow a reaction will happen.
So, we've seen how a single, simple number is actually a powerful code that describes the entire chemical reality of a solution. It's pretty incredible, right? It just makes you wonder, if this one little scale can tell us so much, what other simple, elegant codes are out there quietly running the world all around us?